In an acid-base neutralization reaction, the process that takes place is pretty well described by what the name says. To begin with, you start with an acid and a base. To end with, the acid and the base neutralize each other. And when they do that, the chemical products that form are always water molecules, or H2O, and salt molecules, or in other words, an ionic compound. All acid-base neutralization reactions follow this general type. They start with acids and bases, and they end with water and salt molecules. Exactly what the acid, what the base is, and what exactly the salt is depends on your specific chemical reaction. One way to think about it is to think about the general form. If we're going to start with an acid and a base in reaction, one way to consider that is to imagine the acid as being hydrogen bonded to something else. Acids are defined as acids because they dissociate or donate hydrogen ions into solution. So we'll represent our acid as being hydrogen bonded to something else, and we'll represent that with a black box because right now we don't know what it is. A base can be defined as something that increases the amount of hydroxide in a solution. Hydroxide, or OH-, would also be bonded to something to equal out that minus charge. So we can represent that as OH bonded to something else, which we'll call a white box. Notice the white box comes first because OH is a negatively charged anion, so it would have to be bonded to a positively charged cation. Now that we have this general form, you can see right away where the water molecule comes from. The hydrogen from the acid and the OH from the base come together to make a water molecule. And the salt that forms is actually just the stuff that that hydrogen and hydroxide ion were bonded to. In this case, we always write the cation first, and the cation was the white box. So I can represent the general form of an acid-base neutralization reaction just by putting in boxes instead of actual atoms or compounds. Of course, many times we need to do this for specific acids and bases. Here's an example. Let's say you did the acid-base neutralization reaction between hydrochloric acid, that's HCl, and sodium hydroxide, or NaOH. If you'd like, pause the video and see if you can complete this reaction by writing the products that form. Another way to look at this is just as the hydrogen and hydroxide and then whatever else is left. So if I look at my acid, hydrochloric acid, I know that the acid part is really the hydrogen, and if I look at my base, sodium hydroxide, I know the base is really the OH. When I put those together, I get a water molecule, or H2O. Water, of course, is a liquid, so I'll write that as its physical state. Now look at the ions, or look at the parts of the molecule that remain. I still have a chloride, and I still have a sodium. So not surprisingly, when I put them together, always writing the cation first, I'll put sodium and bond it to chloride for NaCl. Assuming that this NaCl is mixed in with that H2O, I can call it aqueous because it's dissolved in water. This is the general form of acid-base neutralization reactions. Again, it's always the same form, and you just have to adjust the different chemical compounds for exactly what your specific acid and base was. And that's it. Those are acid-base neutralization reactions. There are virtually an infinite number of ways in which acid-base chemistry impacts our understanding of the human body and our ability to treat it through things like pharmaceutical science. Understanding acid-base chemistry allows us to develop techniques and methods which can help us treat patients or better understand substances that we're working with. One of the most common techniques that's used in acid-base chemistry is called titration. And in fact, titration is even more general than acid-base because it can be applied in many different settings for many different reasons. In a nutshell, all that titration is a technique in which you use a known solution, like something out of the stockroom, to determine the concentration of an unknown solution. And like I mentioned, it really is used in many different settings for many different dissolved solutes. For instance, if you wanted to analyze the Spokane River water right outside our laboratory door, you could go down and collect a sample and you could titrate it to figure out the concentration of dissolved oxygen to understand how much oxygen the fish have to breathe. Or maybe you want to know how much dissolved heavy metals are in there as a result of contamination. You could titrate the river water to determine that. You could titrate a patient's blood sample to figure out the amount of dissolved solutes in that particular sample. So titration is really a technique that gets used in a lot of different settings. One of the most common ways titration is used is for acid-base titration. There's two ways this can work. One is to use a known acid to figure out the concentration of a base. The other is to use a known base to determine the concentration of an acid. In either case, your goal or your objective is always to determine the concentration of something that you don't know. One of the things we'll do in laboratory, which we'll use as an example now, is we'll actually titrate battery acid, which is used in a lot of different settings, including automobile batteries. Battery acid contains concentrated sulfuric acid, H2SO4. But the exact concentration of the H2SO4 depends on the make, model, and use of the particular battery. If we want to figure out what the concentration of the sulfuric acid is, we can do a titration to determine that. When you do a titration, you start with a sample of what you're analyzing, in this case battery acid. We do not know what the concentration of sulfuric acid in the battery acid is, just that there is sulfuric acid in there. What we do know is how much battery acid we're using, because we had to measure it out. In lab, we'll use 5 milliliters of battery acid, although sometimes you'll use more in other settings. The other important part of doing a titration is a specialized piece of glassware called a burette. A burette is essentially a long piece of glass that allows us to put liquid in and measure how much is added by dropping it out the bottom. If we want to titrate the battery acid, what we'll do is react the battery acid with a base. The base we'll be using in lab is KOH, or potassium hydroxide. But regardless of what the base is, as long as you got it out of the stockroom, you will know the concentration of it, and after the experiment, you'll also know how much volume you had to add. So in a titration, in this case, we'll drop the base into the battery acid a little bit at a time, and as we do that, dropping the base into the acid, it will start to neutralize the acid. We'll continue to add the base to the acid until it's neutralized. And the way we'll be able to tell when that happened, well, there's a couple different ways. In our lab, we'll use a color indicator, which changes color when we hit a neutral pH. Another option is always to use a pH meter, where you can actually see the numbers that represent how the pH is changing. When you're done, you can then use the information from the experiment, specifically what was the concentration of the base, how much of the base did you use, and how much of the acid did you start with, to figure out what the acid's concentration was. And it's really a three-step process that you'll probably find to be very similar to what we did in our three-step gram to mole to mole to gram calculation. Let's look at a couple examples of how to work a titration problem like this one. Let's say that you did this experiment, you titrated 10 milliliters of H2SO4, that would be the battery acid, with 15 milliliters of 2 molar NaOH. That's our base. What's the concentration of the sulfuric acid? You have all the information you need to solve the problem here except for one thing, and that's a balanced chemical equation. The only way titrations work is if you're adding something that reacts with what you already have. Otherwise, there'd really be no reason to add the two together. In this case, we know we have an acid-base neutralization reaction. My neutralization reaction, which is given here, shows me what the balanced stoichiometry, or the ratio between the reactants, is. In this case, I know that for every 2 molecules of NaOH I added, it must have reacted with 1 molecule of H2SO4. Remember, that's the sulfuric acid in the battery acid. Now it's just a simple three-step calculation. The first step is we're going to use the known or the stock solution to figure out how many moles we had to add to the battery acid. So we're going to pick out what our known solution is and use its molarity, that's the concentration, and its liters in volume to calculate the moles of your known. As you look at the question, your known is always the substance which you know both the concentration and the volume of. In this case, there's 10 mils of H2SO4, but I don't know what its concentration is. So my known must be the 15 mils of 2 molar NaOH. Notice too that this value is given in milliliters, and I'm going to need to convert it to liters in order to do the calculation. So I start out with my molarity, 2.0 molar, which I know really means 2.0 moles for every 1 liter of solution. That's my molarity, and in order to get to moles, I just need to cancel liters. I know that I used 15 milliliters, or in other words, 0.015 liters of the solution. So essentially, all I'm doing is multiplying 2 times 0.015. And when I do that, I learn that I used 0.030 moles of my known, which in this case is NaOH. That's my first step. I multiply concentration times volume in order to get the number of moles. In my second step, I relate the known to the unknown using stoichiometry. This is identical to the second step in problems where we went from grams to moles, then moles to moles, then moles to grams. So I have 0.030 moles of NaOH. I'm going to multiply that by a stoichiometric relationship. So moles of NaOH on the bottom to make it cancel, moles of what I'm looking for on the top. In this question, I'm asked to find how much H2SO4, so that's what I'll put on the top. Then I read this information from the balanced equation. I go to my balanced equation. There's a 2 in front of the NaOH, and there's an implied 1 in front of the H2SO4. So I essentially am taking 0.030 and I'm dividing it by 2. And my answer is 0.015 moles of H2SO4. In other words, in this titration, I know that there were 0.015 moles of sulfuric acid that were present. The last step is to answer what the question asked for. That is to calculate the actual concentration and molarity of the H2SO4. Molarity, as we learned in the last chapter, and as we saw already once in this question, is really just the number of moles divided by the number of liters, or it's moles per liter. For sulfuric acid, I've just determined that I have 0.015 moles of sulfuric acid that were present. That's what the titration told me. And if I think back to the question, that number of moles was present in the volume of sulfuric acid I used. When I read the original question, I see that I used 10 milliliters of sulfuric acid. So that I'm going to put in on the bottom. Now I know I have to be in liters to use molarity, so I'm going to convert 10 milliliters into 0.010 liters. When I divide 0.015 by 0.01, I get my answer, 1.5 molar H2SO4. So just by adding together NaOH and battery acid, or H2SO4, and measuring how much of each I needed, I was able to determine that the concentration of the battery acid was 1.5 molar H2SO4. And don't worry, if the question doesn't use H2SO4, NaOH, or you're not sure what the acid or the base is, it can be helpful to know that information, but you can probably pick out the information you need anyway. Let's do another practice. Here's another titration practice question. Let's say 15 mils of 6.2 molar NaOH was used to titrate 5 mils of H2SO4. What's the concentration of the H2SO4? Go ahead, pause the video, and practice working those same 3 steps. Remember, identify your known. It's what you know the most information about. Then do a stoichiometry conversion, and then finally calculate concentration, which is molarity. Okay, so in my first step, I'm really trying to find moles of my known. When I look back at the question and I have to pick out what to start with, I think I know the most information about the NaOH because I see that I have 15.0 milliliters of 6.2 molar NaOH, and then all I know about the H2SO4 is that I have 5 milliliters of it. So I'm going to start out with the NaOH. That's my known solution, or my stock solution. My first step is to figure out how many moles of the NaOH. I know I have 6.2 molar, which is the same thing as writing 6.2 moles of NaOH per 1 liter of solution. In order to isolate moles, or in other words to get moles alone, I'm going to multiply times the volume. In this case, my volume was 15 milliliters. I need to cancel liters, so I have to change the 15 into liters, 0.015 liters. So I get 6.2 moles times 0.015 liters gives me 0.093 moles of NaOH. That's my first step. My second step is to use stoichiometry. If you got stuck on the first step, pause the video now and see if you can do the second step on your own. My second step is to use the stoichiometry. So I'm going to start with what I already figured out, 0.093 moles of NaOH. And like any stoichiometric relationship, I'm going to put what I have on the bottom to make it cancel and what I want to change it into on the top. The question's asking about H2SO4, so that's what I'll put on the top. I get this information from the balanced equation. There are 2 moles of NaOH for every 1 mole of sulfuric acid. So 0.093 divided by 2 gives me 0.04, and we'll round for sig figs, 0.047 moles H2SO4. If you didn't round, it's okay. It's always okay to round in our very last step. Now I know how many moles of sulfuric acid were present. For my last step, I need to calculate the molarity. If you got stuck, or if you want to try again, pause the video and keep going on your own. For number 3, I want to find molarity, which I know is the number of moles per liter. My number of moles is what I just determined, so I'm going to plug that in, 0.047 moles of H2SO4. And then the liters was given in the original question. It said it was required to titrate 5 milliliters. So 5 milliliters, which I need to change into liters, is 0.005. It's okay to do that in your head if you're comfortable with it, but just be careful to make sure you do it right. 0.047, or 0.0465 if you didn't round, divided by 0.005 gives me a total of 9.4. So I'm going to write that down. I guess you could get a slightly different answer if you rounded, but it wouldn't be enough to justify taking off any points. So I'm going to say 9.4 molar. You could also write that as 9.4 moles per liter. And again, that's the concentration of H2SO4. There are plenty of problems in the textbook that work through these type of titration questions, so be sure to practice them and ask questions as soon as you have them. One of the other most important topics in acid-base chemistry is the presence and the use of what's called a buffer solution. Buffer solutions can arise naturally. We can also produce them in a lab when we want our experiments to take place under certain conditions. Those conditions are conditions where we want the pH to remain relatively constant. So imagine this scenario for a second. You have a pure liquid or you have a solution and you start adding base or adding acid to the solution. Let's say that originally you have a pH of 7. If you were to add acid to that solution, we know that acids have a pH lower than 7, so depending on the concentration of the acid, how much you added of it, and other variables, we expect the pH to go down. Maybe it goes down to something like 5. Again, we'd have to know a lot more information to be sure about it, but the one thing we know for sure is that the pH will go lower. If you had something that's called a buffered solution or a buffer instead, this is a solution that actually resists changes in pH. So if your buffered solution also started at a pH of 7 and you added the exact same amount of acid, everything the exact same, we'd expect the pH to change much less significantly, maybe to something like 6.8 or 6.9. Again, exactly how much it changed depends on a lot of different variables, but we know for sure that a buffered solution will resist changes in pH. It's not that it stays absolutely constant, but it's far less susceptible to the addition of acids or base. We could do the same scenario if you add a base. If you added a base to that pH 7, again depending on exactly what it is and how much you add, maybe your pH goes up to 9. In the buffered solution, we'd expect a much smaller change in pH. And like I mentioned, there are solutions that naturally exist both in the human body as well as in the environment that are naturally buffered. There's also times where we make buffers because working in a laboratory, we want to make sure that the pH of our solution doesn't change. If you're going to prepare a buffer, there's 2 compounds that are the bare minimum that are required to make sure it works. When we come to understand how buffers work, we'll see that there's a reason you need 2 compounds to make a buffer. And in fact, a prepared buffer, meaning something you make up in the laboratory to use in a research setting, only needs 2 compounds to be a perfectly working and functioning buffer. In nature and in our human body, we'll often see buffers that contain more than 2 compounds, but though all of the compounds that are involved are really fulfilling 2 different roles. So the first compound, or the first role at least, in any buffer is a weak acid. Remember, as we saw earlier, a weak acid just means an acid that donates hydrogen ions, but not 100% of the time. And the information that would indicate something's a weak acid is its acid dissociation constant, or Ka, is less than 1. When we're dealing with a weak acid, or any acid for that matter, we know that we have hydrogen bonded to some other atoms or another molecule, which we represent with A. And because it's an acid, it will donate or dissociate from the hydrogen ion, leaving behind the remaining atom or molecule, which is A-. The reason we need a weak acid is that HA, or our weak acid, doesn't dissociate and doesn't donate 100% of the time. So there will always be and always have present some of the HA. If we had put a strong acid in here, the HA would all donate, it would all dissociate, and I'd have nothing left but the products H+ and A-. I need the weak acid there. I need the HA. The reason being, this way, if any base is added to the solution, the weak acid is there to react with it. Again, if the weak acid wasn't there, I could add base and there'd be nothing to neutralize that base, and that would defeat the point of having a buffer. So the first part, or the first compound that's needed in all buffers, is a weak acid. It's there to react with any added base. It's there to neutralize the base, to help keep the pH constant. The second compound, or the second part, is actually the conjugate base of the acid. And that's because, if you think about it, if we have an acid to neutralize bases, we must need to add a base that will neutralize any added acid. But I can't add just any base. If I added just any base, or even a weak base, to this particular acid, most likely they're going to neutralize each other, and then I don't have anything remaining to act as a buffer. So I need to pick the only type of base that won't automatically neutralize the weak acid that's part of my buffer. And that's the conjugate base of the weak acid itself. That's actually A-. So by using the conjugate base of that weak acid, I'm guaranteed that there will always be an equilibrium. That equilibrium or balance will mean that the weak acid is always present, and my conjugate base of the acid is also going to be always present as well. So if I have a beaker in a laboratory I'm trying to do research in, and I want to make sure it's at one particular pH, by adding a buffer, I'm guaranteed that any acid or any base that makes its way into that beaker will be neutralized by either the weak acid or the conjugate base of the buffer. There's one caveat to this, and that's that you'll notice the conjugate base, like most conjugate bases, is in the ionic form. It has a negative charge, and we know that ions are usually found in aqueous solution rather than as their own solids or pure substances. For that reason, when we add the conjugate base, we usually add it in what's called its salt form. The salt form simply means we're going to take the A- and bond it with a positively charged cation so that we can have a solid ionic compound. For instance, if I'm dealing with the weak acid acetic acid, CH3CO2H, I know that its conjugate base is CH3CO2- because we practiced writing that before. But the salt form of that CH3CO2- is simply bonding it with any positively charged cation. So I could choose to do NaCH3CO2, or something else with a positive 1 charge, like potassium with CH3CO2. Any of those would be acceptable options, and that's the most likely way we'd see it in a lab. So in order to mix up a buffer, if you want to make it yourself, you would go find a weak acid, you would go find the salt form of the conjugate base, and using some calculations, you would know exactly how much of each to mix together to get the particular pH you want. If you're not dealing with a prepared buffer in the lab, you might actually be looking at a buffer that established itself naturally in the environment or in the human body. Natural buffers always contain at least 2 compounds as well. And like I mentioned, when they have more than 1 compound, those compounds are still fulfilling the same roles as a weak acid and the conjugate base of that acid. Your bloodstream, for instance, is buffered to make sure that the pH doesn't change significantly, even though you're exposed to a wide variety of different sources of acids and bases every day. In its most simplified form, we can think of the bloodstream buffer as taking place between the weak acid, carbonic acid, and the conjugate base of carbonic acid, which is called bicarbonate. This is naturally present in the bloodstream, and it's also similar to the buffer that's present in many freshwater rivers and lakes. The way that this buffer manages to keep the pH of your bloodstream relatively consistent is that any base that's added reacts with the carbonic acid to become neutralized. So if you take a whole lot of antacids, or you're exposed to any other physiological conditions that increase the basicity of your bloodstream, the carbonic acid can react with that base to neutralize it. Meanwhile, if something happens and you start to experience acidosis, where you start to have increasing amounts of acid in the bloodstream, that acid can be neutralized by the bicarbonate because it reacts and drives this equilibrium in the other direction. So there's many different ways to think about these buffers. Their acid-base chemistry, their equilibrium chemistry, their even Le Chatelier's equilibriums. The most important thing to remember is that the whole role of a buffer is to try to keep the pH relatively close to its intended or original value.